All right, take two on this. I screwed up the first one, so I got to do it again from the start. It's time to talk about gravitational potential energy. This is the way that we use gravitation quite a bit, and we can show some very interesting things when we're done here. First off, when we defined potential energy before, we had the surface of the Earth, we had some sort of object like a box or whatever, and we would lift it up a distance h against gravity. And the potential energy was equal to the work done in lifting this thing up, which was the force times the displacement. Now the force was the weight of the box. That's the minimum force you have to exert to lift something. And the displacement was the distance h. Therefore, we got a very simple formula, m times g times h. But that assumes that the force stays constant. And near the Earth's surface, that's a reasonable assumption. But if we're going to get large and be very far from the Earth, that's not going to be the case. So here's a picture of the Earth, and this is the radius of the Earth. And I have some sort of object here, and I'm going to lift this all the way to infinitely far away. Now the potential energy is going to be the work done, which is going to be the integral of the force, because it doesn't stay constant, times the incremental distance. And I'm calling it r. And the reason I'm calling it r is because we're going to be moving along the radial direction out here. Now the force is the force of gravity, and because the force of gravity is attractive, we should be writing it as minus gmm over r. There's a couple different reasons why you need to put this minus sign here, and mainly because it works out well at the end. But we can talk about why it is you need to put this minus sign here. But this means an attractive force. If you have a positive force, it's generally considered a push. A negative force is considered a pull. I often forget these things because we're just working in magnitudes and we draw a free body diagram to figure out the direction. But in this case, it's important to put it in there. So now we put that into our equation, and we are going to do an integral. It's going to start at the surface of the Earth, it's going to end at infinity, and it's going to be of minus gmm over r squared dr. Well, everything factors out except for r to the minus 2 power dr. And since this is and I've left off the limits, I'll put them back on when it's important. Since this is a polynomial here, it's just a r to the minus 2 power, we know how to handle this. You increase the power by 1, and you take the new power and you multiply by that. So that's multiplying by minus 1. So that's going to cancel this minus sign, and the work done in lifting this thing is going to be g mm, and now r to the minus 1 is the same as 1 over r, but that needs to be evaluated between the radius of the Earth and infinity. So that's g mm times 1 over infinity minus 1 over the radius of the Earth, and that turns out to be that the potential energy is minus g little m capital M over the radius of the Earth. Or in general, if we were to start somewhere other than the surface of the Earth, if we were to start up a little higher and go, it would just be that radius. As long as the radius isn't inside the Earth, that would change the force. So as long as we're outside of the Earth, the potential energy is minus g m over r. General result. So the potential energy looks just like the force law. Oh my, look what I did. I didn't put the squared here. Who let me do that? You're not here to keep me from making mistakes. Okay, so the force law, they tell you the potential energy looks just like the force law, except that it's negative and it depends on r. The other thing that's cool about it is that it's a scalar, which means we're going to be able to use it very easily. All right, so let's remind ourselves of that, and let's make some notes here. So potential energy, gravitational style, is now going to be minus gmm over r. And the notes on that, oh no, let me turn, are that, first off, potential is 0 at r of infinity. That means that our reference point is infinity away from the Earth. Other notes, u is negative. You see, if you drop something near the Earth's surface, it has a high potential energy, then it drops down to a lower potential energy. It loses potential energy. But if you're starting infinitely far away at zero and you fall towards the Earth, you are losing potential energy. You're going into negative territory. All potential energies are negative. That's not a bad thing. It works just fine. If you subtract the potential energy at any 2 points, it still works out the same. And what was the other thing that I was saying? Oh, yes. U is a scalar, which means if we were trying to do some vector math here, if we were trying to say, okay, I've got 2 planets, one here and a smaller one over here, and I'm in a little spaceship right here, I would be heavily attracted towards this planet and only slightly attracted towards that planet. And so I would have to combine these two in a vector way, and they'd have to be done into components. These are the forces. But if I want to solve the same problem using potential energy, it's significantly easier. I simply calculate the potential energy from planet 1 and add to it, oh, where's the other planet? Over here somewhere. The potential energy from planet 2. It's just a sum. So the total potential energy for any arrangement is the sum of all the potential energies for the different individual pieces in that arrangement. It's a scalar. You just add it up. It's so cool. And since all of them have GMM or GM in them, it's really just an M over R kind of thing that is different. So that's a lot of fun. We need to prove that this works near the Earth's surface to give us the same result. So now that I've talked about this, let's carve out this section of the paper here. So for small trips near the Earth's surface, we need to figure out what the thing is. So let's we got a curving Earth. We're going to start at the surface of the Earth, but we're going to move up here, and we're going to move up here a distance h, and h is a small amount. That means our change in potential energy is going to be a minus gm mass of the Earth over Re plus h. That's our finishing potential energy, minus a minus gmm over Re. That's our starting potential energy. The change in potential energy is final minus initial. Minus a minus is a plus, so I'm going to put this term in front and subtract that term from it. So that's going to be GMM, and then we're going to have 1 over Re minus 1 over Re plus H. Now, this is a difficult thing. We're subtracting something and we don't have a common denominator. So I'm going to go ahead and use the poor man's common denominator. Let's move over here. GMM, and the poor man's common denominator is the product of these things. So what we're going to have is we're going to have R plus H over Re squared plus REH. That's the product of these two. Minus, and then the other thing is going to be Re over Re squared plus REH. And this Re plus H minus Re is going to give us just an H on the top, and on the bottom is going to be Re squared plus Re times H. And here we can exploit the fact that H is very small compared to Re. So Re is huge when it's squared, and Re times H is just kind of nothing. You know, a big number times a small number. It's a medium-sized number, but that's huge. So as long as H is really small compared to Re, we can ignore this term, which gets us back to G M M times H over Re squared, which is little m times G, because G is capital G, capital M raised to the earth squared, times H. So I have proven that that this small trips near the Earth's surface, this particular equation for potential energy with the proviso that we can ignore a very small h compared to Re, this works. If you don't believe me, figure out the difference between the percentage difference between this and that for a height of say 100 meters and the radius of the Earth of 6 million meters. You'll see what's going on. Okay, moving on. Let's talk about escape velocity. Okay, so now we're going to get into some really fun stuff. Escape velocity. How do I escape from the Earth? If you throw a rock up into the air, it eventually stops and comes back down. If you shoot a rocket up into the air, it should stop and come back down. But if we throw it fast enough, it will escape. How do we get it to escape? Well, what we want to do here is we want to have our rocket, and this is going to be a bullet style rocket. It's not going to continue to have thrust. It's going to have thrust at one point. We're going to give it one speed, and it's going to have a speed, which means it's going to have a kinetic energy, and it's going to have a potential energy at that point. And we want this rocket to make it all the way to infinity. Okay, it's a bullet, not a rocket. And at that point, it will have a kinetic energy of 0 and a potential energy of 0. So what we need is the kinetic energy plus the potential energy at the surface of the Earth to be equal to 0. Okay, that means we need 1/2 m v squared to be equal in magnitude, because this is going to be negative and this is going to be positive, so adding them together will cancel out to 0. We need to be equal in magnitude to g m over re. The little m is the mass of the projectile, so it cancels out. 1/2 goes to the other side, and we have that v squared equals 2g capital M over re. And that means that the escape velocity for any planet is the square root of 2g, mass of the planet, divided by the radius of the planet. Pretty cool. Keep this in mind. It's going to be important later. I'm going to circle this one because I need to be able to find it, because we're going to do some more stuff. Okay, if we're going to throw rockets into the air, what about if we don't throw it quite far enough for it to get to escape? What if we only throw it far enough that it goes into orbit? So we want to figure out what orbital velocity is. And there's actually an easier way to figure this out. Orbital velocity, that means how fast in order to have a circular orbit. Well, we can just draw a circular orbit. Here's the Earth in the middle, continents and stuff, and then our orbit is going around in a circle around the Earth. We have a satellite or something like that going this way. Well, what we know here is we know that this is circular motion, and circular motion means that the force of gravity has to be equal to the centripetal force. So this one's actually done better with forces than with the potential energies, but I'll show you how the energy works out. And maybe we put these in absolute values, because I know I made a big deal out of this one being negative. Really, that's just the direction. We want the force of gravity, which is towards the center, to be the centripetal force. Force of gravity is g, little m, big M, over the radius of the orbit squared. That's not the radius of the Earth, that's the radius of the orbit, much more than the radius of the Earth. And over here, we have mv squared over r. Get the chainsaw cancellation going, because that means that this r cancels this square, this m cancels that m, and what's left is that v squared is gm over r, or the speed of an orbit is the square root of capital G, capital M over r. And you'll notice that this thing is related to this thing. It is the same form, same factor, only there's not a 2 underneath. So it's 1.4 times faster to escape from the gravity of the Earth than to go around in an orbit. Now, that's not the entire thing here, because obviously in this case we're going around in a circle with a tangential velocity, and in this case we have a radial velocity we want to escape to infinity. But it is kind of interesting the way that they are related to the same thing. It is instructive at this point to take a look at the energy of an orbit, the total energy of an orbit. So, what is the energy of an orbit? In other words, what do we have to do to get something up above the Earth and then get it to turn to the side and go around. So let's draw our picture here. We have our little Earth, and we're going around it at our orbital velocity. And that means that we have both kinetic energy and potential energy at that point, whatever the radius of this orbit is. This black pen needs help. Okay, so the kinetic energy part of it is easy. It's 1/2 mv orbit squared. And v orbit had a square root in it, so that's going to unsquare root it. And we're going to wind up with 1/2 gmm over r. Or I guess I could just write it as gmm over 2r. But the potential energy part of it is going to be minus gmm over r, which means that the total energy, typically abbreviated E, is going to be K plus U, which is going to be, let's see, we have half as much plus negative that much. It's going to be negative gmm over 2r. That is the total energy of an orbit. Notice that it is, we have half as much kinetic energy as potential energy. That's important. And notice that the total is negative. And that means these orbits are bound. They cannot escape. They're underneath the axis on the potential energy curve that we learned to read last semester. So the work done to put something in orbit is K plus U. And that's going to be 3 gmm over 2r. It's 1/3 kinetic energy and 2/3, 2 helpings of potential energy. So you spend 2/3 of your rocket fuel getting up to the orbital location, and then 1/3 more of your rocket fuel to get it going to the side at the correct speed to be in orbit. Of course, we don't generally fly straight out, then take a left turn and go this way. We do this all as one thing, but we need to get up to this altitude with the appropriate sideways velocity to stay in orbit. Okay, let's take another step here. This is a really weird and wacky world of orbital mechanics here. And I'm going to link to a Scott Manley video that talks about orbital mechanics. But let's just assume here for a second, what happens if you speed up or slow down while in orbit? Hello. I think it helps if I show what I'm writing. Let's put a question mark at the end of that. So here we are, very high above the Earth, going by at a certain velocity. What happens if we slow down and speed up? Well, if you fire your thrusters forward, I mean, point the rocket motor the direction you're going and fire your thrusters forward. Retro rockets, they call that. You will slow down. If you slow down, your kinetic energy will drop. If your kinetic energy drops, your total energy will drop. And the orbit moves in. You will drop into a lower orbit. You will drop into a lower orbit, and then as you drop into the lower orbit, you will speed up because you're losing potential energy, so you'll gain kinetic energy to add up to this new lower total energy. And what will happen is you were going around in a circle. you will now drop below that circle. And when you get halfway on the other side, you'll be at your lowest point and you'll be going faster. So you'll move out away because you're going too fast for that lower orbit, and you'll have an elliptical orbit that is inside of the old circular orbit. I've always found it very interesting that the way it works is you are halfway around the orbit when you get to the lowest point, and then you get back to your original point here. It's kind of like oscillatory motion, in and out, in and out. And I always thought, well, why does it have to be exactly on the other side? And I've yet to have a good explanation for you for that, but that is what happens. Then what if you fire aft thrusters so that you speed up? Well, your kinetic energy will increase momentarily, which means that your total energy will increase momentarily, and the orbit moves out. Well, once again, here's our planet. Here's our original circular orbit. That was not expected. And what's going to happen is we're going to move out away from our orbit because we're going faster now. Move above. Now we're moving too slow for that orbit, so we come back in, and you do this. You get a larger orbit, and this is also an ellipse outside of the circular orbit, but it intersects the circular orbit at that one point. So if you really want to drop into a smaller circular orbit, it's really interesting what you have to do. You have to fire retro rockets to slow down to drop in, and when you get to the new orbital position, you have to fire retro rockets to slow down to the correct speed for that orbit, because you will have picked up enough speed dropping to a lower position, trading potential energy for kinetic energy, that you're now moving too fast for this lower orbit. So you slow down to drop in, and you slow down to stay in the smaller dropped in one. And then this one, you fire your rockets forward to go to a larger orbit, and when you get to this point, you're going too slow and you're about to drop back down, so you fire your rockets to the aft again to go fast enough to stay in this larger circular orbit. Everything about orbital mechanics is backwards. You have to slow down to go closer to the Earth. You have to then slow down to stay closer to the Earth. And it just seems odd, but because of all the trading of energy between potential and kinetic, that's how it works. Notice that you're never thrusting towards the planet. That doesn't do anything for you. It's always slowing down and speeding up. So that's kind of fun. I'm going to let you watch the Scott Manley video that is tagged in the Google Classroom feed.